Happy Respiratory Care Week. So today, first of all, I want to thank Keith and Respiratory Associates for, inviting me to give this lecture and kick off Respiratory Care Week for y'all. Today, we're going to be talking about AI. We're going to talk about a little bit about the history of it, a little bit about what it is, and I thought I knew, and then I did research. Apparently, I was way off. And then we're gonna see how it applies to healthcare in general, and then we're gonna take a closer look at healthcare just in the lens of mechanical ventilation. So, first of all, let me get my conflicts of interest out of the way. I am a current clinical application specialist for Hamilton Medical. So I am an employee from Hamilton Medical. Normally, I do try to deliver content that is not product specific or company specific. I try to teach things that can be utilized on any ventilator on any platform from any company. Today, though, there are limited things to talk about with AI in terms of mechanical ventilation. And Hamilton Medical is one of the couple that's actually making strides in this front. So it's going to be a little bit more product specific than I normally get into. But I do want to make you aware of my conflict of interest. And let's continue on. So first thing I want to talk about, Respiratory Care Week. Let's get it. This is our week. This is our week. It's the week where everybody shows us how much they appreciate us and let us know that we are not forgotten clinicians. Although, when you meet people out in the world, hey, what do you do for work? Oh, I'm a respiratory therapist. They think you're someone who talks to people about how to breathe properly. And then you have to tell them it's about mechanical ventilation, ECMO, CPR, intubation, blood gases, like the myriad of things that we do. And there's not a lot of popular culture references to respiratory therapy. In fact, there's pretty much none. But if you want a pop culture reference to respiratory therapy, even if you don't listen to heavy metal, I'm pretty sure that everyone is familiar. There's a subgenre of rock music called heavy metal. And there are several bands that brought this into popularity in the 70s and 80s. One of them is Slayer. And the lead singer, Tom Araya, is a respiratory therapist. He worked at Kaiser Permanente Baldwin Park in the 1980s, and he was actually the only person in the band who was gainfully employed. So it was his RT money that funded the recording of their first album. And now he's a rock legend. So we can count Tom Araya in the ranks of us RTs. He actually gave a very nice interview in Loudwire magazine a couple months ago, actually last year, and talking about his life before being a heavy metal star. And he talked about being a respiratory therapist and how he was intubating and drawing blood gases and managing mechanical ventilators and how much he enjoyed doing that profession, and how if he didn't make it as a rock star, he'd be very happy doing that today, almost 40 years later. So just keep that in mind. At least one celebrity has their back. All right. So now we're going to get into actual, hold on. It's going to be easier if I use my keyboard here. All right. So let's talk about AI, right? So this is a very lengthy definition, but essentially artificial intelligence is a subspecialty in computer science where what people do is they create systems that are able to process vast amounts of data, which can learn from itself and create new content or solve new problems. And the thing with artificial intelligence is the newer kinds do not need human intervention. They don't even need to give it data with labels. You just give it data and it labels it itself, figures everything out, learns languages, learns to identify things with pictures, much like the human brain. So, oh, good gosh. Yeah, there's always this possibility too. But we'll get there. We'll get there in a little bit. So let's talk about the history of AI, right? So AI first came around in the 1950s, and actually in 1950. And Alan Turing created this test to determine whether or not the machine was considered AI or if it was just a machine built on specific algorithm, right? It's called the imitation game. And what it was you had 3 rooms. In one room, you had a person who's talking to a machine or a computer in another room via text. And then you had a third person monitoring this conversation in a third room. And the test was, if it was considered an intelligent machine, then the person in the third room who was looking at this conversation would not be able to tell who was the robot and who was the person. And this is actually still used a little bit today, the imitation game. And this was the first real test of AI. 1952, Arthur Samuel, actually with the help of IBM, a little startup then, they amounted to something apparently, created this program. It was called the checkers program. And it taught itself to learn how to play checkers. So this is the first iteration of a machine learning a new skill on its own without it being programmed. Then in 1955, you had John McCarthy, who was considered one of the forefathers of artificial intelligence. He actually coined the term artificial intelligence during a summer workshop at Dartmouth College. 1959, Arthur Samuel coined the term machine learning, which we will get into in a little bit, but it is a subset of AI. And it was pretty much the first part of AI that was utilized. Basically, AI is kind of like building blocks. Like first you get machine learning, and then you go to deep learning, and then you go to generative AI. And all these things came about at different time periods. So, but machine learning really comes into play in the 1970s and 1980s. But he coined the term when he was talking about how he was creating programs where he was teaching machines to play chess that are at a level that's actually better than their programmers. And the key word here is teaching, not programming, right? You can program a machine to play chess, but he was actually teaching machines to play chess, which means that they were learning from past experiencing and developing their skill set and getting better. In 1961, GM utilized the first AI industrial robot. This was called the Ultimate Robot. And what it did was it transported die casings and it welded parts onto cars. This is very important because these are jobs that were very early in car manufacturing deemed far too dangerous for humans to do themselves. So the fact that they could institute a robot to help out with these more dangerous tasks was extremely helpful and saved probably a lot of lives and a lot of limbs. 1966, Joseph Weizenbaum created the first chatterbot. We now call them chatbots. You get emails from them, you get text messages from them, you get instant messages from them. They're pretty much ubiquitous across all forms of social media. And now, instead of being called chatbots, most people just call them bots. And then in 1968, Alexei man, his name's a phonetic conundrum. Ivanenko proposed a new approach to AI, it would later become deep learning. And this is essentially where machines started to learn and grow. Basically, you take machine learning and you add multiple layers of that machine learning, and then you get deep learning, which allows it to process more information, make better decisions, and learn more quickly from past experience. And then 1979, James Adam created this thing called the Stanford Cart. And it was able to successfully navigate a room full of chairs without any human interference. So this became the first autonomous vehicle or self-driving. It's not a car, it's a cart, but this is the first iteration of that. And as you can see on the left, you have a picture of James Adams with the Stanford Cart. 1980, you had the first commercially released AI system. It's called XCon, and basically it was a order data entry type of deal where it assisted customers in ordering computer systems by picking specific components that were based on each customer's specific and unique needs. Then around 1984, you had what was called AI Winter, where um, it was predicted in 1984. It actually came to fruition in like 1986 or 1987. But what was predicted was that there would be a decrease in interest and thus a decrease in funding in AI research. And this lasted for about a decade, where people did not see AI as financially or technologically viable, or it would the research and development would cost more than they felt that it was worth. So you had a lull in development for about a decade, maybe 15 years. And then in 1997, this computer program called Deep Blue actually beat the world chess champion, who was at the time Garry Kasparov. Now, this is the first time in history that a computer program was able to beat a world champion of chess. It had been tried before, but the world champion at the time had always been able to defeat the computer program. It's the first time a computer program was able to outdo a world champion at chess. In 2003, NASA built the Spirit and Opportunity rovers and sent them to Mars, where they were able to successfully navigate the planet on their own without any human interference. 2006 was where we started to see kind of AI with what it is now, because companies like Facebook and Twitter and Netflix started utilizing AI not only as part of their advertising, but part of their user experience algorithms. So based on your watching or even browsing history on Netflix, it would recommend movies it would think you would like. And this is all based on AI, looking at the patterns of what you're doing and predicting future patterns, which is what AI essentially does. It looks at a certain pattern and it's able to predict future patterns and future behavior and future events based on the data that it has collected already. And it learns from new data that it's collecting all the time. 2011, we have our good friend Siri still around. It's the first popular virtual assistant. They've had virtual assistants before, but it was more like when you call a company's automated helpline, and you're like, I have a question about my bill. And the AI voice on the other end says, you asked about the weather. Let me tell you the temperature today. And you're like, no, I did not. I did not ask about the weather. But Siri was the one that actually was able to understand language. It's able to understand accents and slang terms. So, and it's able to respond appropriately. So this is why it became widely adopted and so popular. In 2016, Hanson Robotics, they created what was known as the first robot citizen. Her name was Sophia. And not only was she able to communicate in a way that mimicked human intelligence and human response, she was also able to emote, show facial expressions and emotions. And she was also able to learn new emotions by visualizing emotions on other people's faces. 2017, Facebook actually programmed 2 different AI chatbots to converse with each other with the hope that they will learn to negotiate with each other. And what ultimately happened was they developed their own language autonomously and actually foregoing English. They stopped speaking English. They just had their own language that they knew, that they developed together. And that's what they used to converse and negotiate, which is pretty cool because no one taught them this new language. They invented a new language on their own. In 2020, OpenAI started the first beta test for the GPT-3 system, which can create writing poetry and code The thing is, it's no one can tell if it is created by humans or machines. And this is all because of deep learning. So deep learning is where we're going to really start to see giant strides in artificial intelligence. Okay. Oh, good gosh, there he is again. He's always looming in the corner. Whenever we're talking about AI, this guy's always looming in the corner because he is literally the worst case scenario of AI. And if you don't know this is the Terminator from the Terminator franchise movies. Machines in the future, they're AI, they rise up, they kill all the humans, rule the world. So, what is artificial intelligence? So, like I said before, there are different levels to it, right? So, under the overall umbrella of artificial intelligence, you have machine or learning, which became very popular in the 80s. And then in the 2010s, we got to deep learning, which is much more complex, but it uses machine learning to do what it does. And then in 2020s, you get even more complex generative AI. So as far as machine learning, basically it's an algorithm that makes predictions or decisions based on inputted data. Okay. And there's usually one or two hidden layers of data and analysis. Okay. And this is called supervised learning because it uses labeled data inputs. You can't just throw a picture at it or a number or a word and it'll know what to do with it. Right. So the data has to be labeled, like this is static compliance, this is airway resistance, this is tidal volume. You have to label this data in order for it to do what it does. And how it processes this and analyzes it, it uses several different strategies. First one's called linear regression, then we have logistic regression, then you have decision trees, random forest, subvector machines, support vector machines, and k-nearest neighbor. Some of these are very complex, and it took me a while to wrap my head around, but I try to make it as simple as possible to give you kind of just a cursory knowledge of what this stuff is and how it's doing it. So first thing we're talking about is linear regression. And basically what it does, it predicts one variable based on the value of another variable, right? When X does Y, it's always going to produce Z. So if you look here at our picture here, you can tell, you can predict kind of the next plot points in this linear pattern. Where the nonlinear pattern, you can't really predict the next plot point, okay? Whereas on the graph on the left, it's much more easily predictable, okay? That would be linear regression. Nonlinear regression, that's something that we're going to talk about today. Then you have logistic regression. And basically what it does, it estimates the probability of an event based on a whole data set of independent variables, right? The best analogy for this would be the weather, right? Based on past experiences, barometric readings, airflow, right? Wind percentage or what have you. It can predict when it's going to rain, when it's going to snow, if it's going to be cold tomorrow, if you're going to have a heat wave. And it uses previous data to predict future events. And it's a myriad of data too. So here's where we're starting to get into the correlation of just a lot of different data sets, all inputted into one system. And then it makes predictions based on what it's seen in the past, what's going to happen in the future. And the basic, so with linear regression, X does this, it produces Y, always. Whereas here, when X does Y, sometimes it'll produce Z, sometimes it'll produce W. But with more data, it can make more accurate predictions. And then you have decision tree. Now, this should be very, very familiar to everybody on this call because It's used a lot in the medical field. NRP, BLS, PALS, ACLS, all of it uses decision trees, right? And basically it's a flow chart, and it helps you visualize and predict potential outcomes of a series of decisions, okay? And what it does is it compares the cost, probabilities, and benefits of different actions and the outcomes of what they're likely to produce. Next, we have the random forest. So this is essentially just a whole grouping of decision trees where you use multiple decision trees, right? And you input many different types of data into each decision tree, but they all coalesce to produce one result, a single result, right? So you're just taking the decision tree and you're adding, 3, 5, 100, 1,000 different decision trees, all with different data sets, and they're all going to come to help the AI reach a single conclusion. Then you have support vector machines. This one, now we're starting to get into calculus. Calculus is never my strong suit. But essentially what it does is it takes two different data sets and it makes a vector plane in between where the sets mostly diverge. So if you notice over here on the left, you have your green circles, right? And then over here on the right, you have your blue triangles. This one blue triangle wound up over here with the green circles. But we're going to draw our vector plane here to show that even though this blue triangle lies over here, still a blue triangle, but it does rely on a different data set for it. And this algorithm is generally used in detecting spam emails. So support vector machines, that's pretty much what they're used most for, is detecting spam and throwing them in your junk email folder. As far as k-nearest neighbor, what it does is it classifies data points based on the data points that is around them. So if you look at, and k is the number of data points around the data point you're trying to classify, okay? So if you look at our smaller circle, right, we have 3 data points. You got 2 purple circles and a yellow circle, right? And the star would be classified by the majority vote. So 2 purples, 1 yellow, this would wind up being classified as a purple. But if you increase the area to encompass these next 3 yellow circles, now you have 4 yellow circles and 2 purples. So now with the larger radius, the red star is going to be classified as a yellow circle. So basically you're just looking at the nearest neighbors, seeing how many of which type of neighbor there are around it, and then using that to classify that particular data set. Oh, sorry. Yeah, okay. So next we have deep learning, right? So deep learning utilizes machine learning. It takes all the different subtypes of machine learning that we just talked about, and it layers them, and it combines them. So like I said, machine learning will have 1 or 2 input layers. Deep learning will have 3 or more, sometimes hundreds, sometimes thousands of layers. All of them collating data, taking in data, taking in data inputs. And here's where we're able to do unsupervised learning, okay? Where you can put in unlabeled data, and utilizing deep learning, the AI will start to figure out, classify, categorize, and be able to utilize the unlabeled data. This is how machines are able to learn language, or with the 2 Facebook chatbots, create their own language. And this is where we're going to start to really closely simulate how the human brain works, how it processes information, and how it makes decisions. So what deep learning utilizes, or what the uses are. First of all, targeted marketing, right? Based on your browsing history, what you purchase, what content or pop culture you consume, your streaming habits, all of that, believe it or not, all of that is tracked. And all of it is used in algorithms to target you for specific products, services, movies, books, TV shows that it thinks you'll like. It's predicting your future behavior and your future decision making based on past behavior and past decision making. And this is how it's learning you, and it's constantly taking in the data that you put into your phone, into your computer. I don't think we realize just how many times we look something up on Google, or we go shopping for something on Amazon, or we put a movie on our watch list on Disney Plus or Netflix, or we watch something. So AI is constantly taking our habits and what we're doing and putting them into an algorithm where it can show us things that things we'll like and things we want to buy. This is both a blessing and a curse. Blessing, I'm finding awesome stuff to buy every day because of this. Curse, spending all my money on it. Other uses, fraud detection. So it looks at your spending habits and where you're doing those spending habits, right? So, sees me go to the Whole Foods a mile down my street, spend $150 on Tuesdays and Thursdays. Okay, so if it sees another charge for $150 at Whole Foods on, next Tuesday or next Wednesday, it's going to say, not out of the realm of possibility. He goes to that place often. It's fine. Whereas he sees me spend, or it sees me spend, money at Whole Foods, then across the street at CVS, then buy a coffee a little bit down the street at Starbucks. All those are fine. All those would be within my proximity and within my habit. Whereas if it sees all those charges and then it sees I spent $150 at a Target in New Mexico an hour later, it's going to think something's up, because that could not be predicted by the algorithm, right? Unless it knew that I was traveling to New Mexico. But if it doesn't see that, just sees a random charge in a random place where it knows that you couldn't possibly get to in that amount of time, that's when it raises the right flags and say, hey, this might be a fraudulent charge. I don't think this person made this charge. Based on their previous spending habits, this is not something that I could predict. So this is how fraud detection happens. And it's constantly, the algorithm's constantly learning from your spending habits. It's looking at you constantly, your credit cards, your ATM debit cards. It's looking at your spending habits, and that's how this is figuring out whether or not you committed fraud or not. Now we have generative AI. Ooh. This is where we're actually going to simulate behavior of the human brain, right? And this is where you teach computers to learn from examples, right? This is where they get image identification, language translation, pattern recognition, decision making. All of this starts to happen at the level of the human brain, because we're taking more layers of machine learning and now deep learning to create generative AI. And these things can, by looking at previous content, say you want to write a sci-fi book, right? And it would look at previous sci-fi books and then would use that previous data to create its own independent original work. And the thing is, nowadays you cannot tell what's created by a human and what's created by a machine, because it's very similar to what it's seen, but it's not identical. As far as generative AI tools, most of these I've never heard of. Apparently they're popular, but there are 3 different types of generative AI. The first is variational autoencoders, and it generates multiple variations of content in response to a prompt, a specific prompt, right? Like, say, paint me, what did I see one time? Paint me a picture of a virus dancing the tango. And instead of producing just one picture, it'll produce multiple pictures in different styles, say one in Renaissance style, one in abstract art, one in surrealism. So that's what essentially that does. And then you have diffusion models, which they generate new content by adding random noise to the image or the data. And then they slowly take away that noise and use the different levels of noise to create new original content. Then you have transformers. So basically what a transformer is a type of neural network that transforms or changes an input sequence into an output sequence. And they do this by learning context and tracking relationships between sequence components. Okay. So how generative AI works, right? It's training, it's creating a foundation model, then it's tuning, right? This is adapting the model to specific application or applications. Next, it's evaluating and tuning some more. So to improve accuracy, it is continually adapting, evaluating, more tuning, adapting, evaluating, more tuning. And this is how the machine learns and is how to do what it does. So some of the benefits, automation of repetitive tasks. You get more and you get faster insight from data that you input into it. There's fewer human errors, especially like fraud detection, stuff like that. And then it's available 24/7. It's always working. It never has to sleep. Oh, good gosh, there he is again. Are you guys tired of him yet? Because, you know, he's going to hang around for the rest of the time. AI in healthcare. So diagnostics, you have radiology, right? So deep learning can allow AI identification of so many different maladies and diseases, all with X-ray, CT scan, MRI, PET scan. And again, this is the deep learning. It's going to take all these different images, all these different maladies, analyze them, and look for patterns, right? Just like the human eye is trained to do, right? You know a bone fracture when you see one. You know how many ribs are expanded. You know if your diaphragms are flat, your heart is enlarged. If it's not, you can tell the pneumothorax. And so, we've all done this at school. You had a hard time, but then after seeing multiple X-rays of the same thing, you learn to pick them out very, very quickly. And this is essentially what deep learning does. For breast cancer, there's a company called Profound AI. And basically it looks at mammographies and it will pinpoint circle areas of concern. So it delivers a confidence level as well as pinpoint and circle it. And what the confidence level means, say you have a confidence level of 92. That means 92% of the cases that look like this were ultimately proven to be cancerous, right? So if it's like 10%, probably not anything to worry about, right? 92%, probably a little reason for concern. And this is currently FDA approved. So I don't know if it's on the market yet or if it's coming to market, but you can expect to see this either now or in the future. So for stroke, there's this app called Viz.ai. And what it does is as soon as a CT scan of a potential stroke victim is done, it immediately looks at it, determines whether or not it is a stroke, and it also starts to mobilize resources and it schedules its own procedures. So it'll start paging practitioners, it'll start paging doctors, neurologists, and it'll start booking OR rooms all on its own. Improves efficiency, improves timeliness, and that is the name of the game with stroke management and stroke treatment. You got to detect it early, you got to treat it early, or there's death or just poor quality of life. So the quicker you can get a handle on this, the better the patient is for it. And Viz.ai makes this almost instantaneous. As soon as a scan is taken, it starts the ball rolling. Drug discovery. So drug discovery, pretty much every drug class, all the drugs in it look pretty much the same. There's just like little tiny differences in the exterior molecules and functional groups. Okay, and let's take antihistamines, right? So antihistamines as a class 30 years ago tired you out because they were lipophilic molecules, which means it's able to cross the blood-brain barrier. Most of the things that cross the blood-brain barrier make you drowsy, right? Anti-epileptics, antipsychotics, they all just floor you. You're so tired on them. And it's because they're able to cross the blood-brain barrier. But the difference between those and antihistamines is antipsychotics, anti-epileptics need to work in the brain, whereas antihistamines don't. So Claritin, I can't remember what the precursor was, but basically this company took their antihistamine that made you drowsy. They added an alcohol group on it to make it polar and not lipophilic anymore. Made it hydrophilic. Now it can't cross the blood-brain barrier. Now it doesn't make you drowsy. And then every other company that made antihistamines saw that and I said, oh, I'll just slap an alcohol group on my drug, call it something different. Now it doesn't make you drowsy. Now you have Allegra, Zyrtec, right? And they're all old antihistamines that made you drowsy. They're just made polar so that they can't be absorbed by the blood-brain barrier. And this is how AI is going to utilize this. It's going to look at side effects. It's going to look at the receptors and what type of molecules needed to activate that receptor and induce that effect. And AI is going to help us a lot with that. The first iteration was actually for the COVID-19 treatment, Paxlovid was used by AI to develop that drug. That's why it was able to be developed so quickly when the pandemic hit. Home care, right? So there's a company called Bioformis. They use a wearable patch. And what this does is it monitors your vitals. It can send text messages to your phone, alerting you if you need to go back to the hospital. It can do virtual visits. And because of this, hospitals can discharge patients they would normally have to keep for observation much earlier. There's a company called Freenome, uses AI and just regular diagnostic blood work. Like you could go for your physical and you get your blood work, your CBC and all that. This will also test for cancer to a very high level of accuracy to try to catch diseases and conditions very early, because the earlier you can catch things, the more easily they are to treat. Oh, good gosh, this guy again. IBM. So 2011, they created a program called Watson, an AI program. And this program, Watson, absolutely decimated two of Jeopardy's all-time champions. They're like Jeopardy's best all-time champions. It just tore them apart in Jeopardy. And it was the first AI to actually do this. So now what IBM has done is they've transferred Watson to be used in the healthcare setting. So it improves treatment, it enhances patient engagement, right? It can develop personalized health plans based on each individual patient, can interpret genetic results, and it's very good at catching signs of early disease. All right, so lastly, mechanical ventilation. Now, I want to preface this by saying I was very disappointed in my research because I wanted to showcase not just Hamilton Medical, but I wanted to showcase all the ventilator companies out there right now, and the strides they're making to improve patient outcomes with AI. As it turns out, there's only really 2 ventilator companies that are using it. So very quickly, Draeger, not much in AI. They have minimum mandatory minute ventilation, MMV, as a mode. I looked into that to see if it was AI. It's not. It's just a threshold system where you set a mandatory minute ventilation or mandatory minimum minute ventilation, and then you actually set your tidal volume and your pressure or your pressure support and your flow trigger and all that stuff is set by the user. And basically, if the patient's breathing spontaneously, if they exceed that minimum mandatory minute ventilation, it'll automatically wean the SIMV rate, because essentially it's an SIMV algorithm. Whereas if the patient falls below that minimum value, it's going to ramp up that SIMV rate to help hit that minute ventilation. And it's just a threshold system, right? If X happens, produces Y. Same thing with Servo and Gentinge. They have what's called auto mode, where when it senses X amount of spontaneous breaths in a row, it will automatically flip into a spontaneous mode. This is fantastic, right? I'm not trying to discount MMV and auto mode because they will drastically help improve patient care and weaning, help get your patients off the ventilator much, much quicker, but they can't be classified as AI. Because, again, with auto mode, it is a threshold system, right? When X happens, it goes to Y. Next, you have Neon Codon. I looked at their Gentle Lung software because I was hoping that it would analyze the lung data from laminar flow, slow flow, pressure volume loop, determine if the patient was recruitable. If so, would recruit them, and then would do a decremental PEEP titration, finding the optimal PEEP, which you can do on there, but it requires input and analysis from the end user. It doesn't do it all on its own. It doesn't learn from previous experiences. Basically, you put in the numbers, when you want to do it, how you want to do it, how long you want to do it, and then it'll do the maneuver, and then you have to analyze the data and then go from there. Which brings me to closed loop ventilation. So two companies have it. There's Vyaire and there's Hamilton Medical. And this essentially uses machine learning functionality, right? For Hamilton Medical, we call it adaptive support ventilation. Vyaire calls it AVM, or adaptive ventilation mode. So they work pretty much the same way. Like as I was researching AVM, or adaptive ventilation mode, I was like, oh my God, it's almost exactly like ASV, or adaptive support ventilation for Hamilton. Now there are differences in performance because the hardware itself is different. And there's a little tiny difference in algorithm, which I'm going to go over later. But I'm going to utilize my ASV slides because I had them readily. I can speak to them. But just know the AVM follows the same basic principles I'm talking about. So for the next several slides, you're going to see a lot of stuff about ASV. You can also put AVM into this as well. So improve patient outcomes, right? So we have conventional ventilation, right? You got the patient, you got the clinician, right? Assessment of physiological status. So we look at all the plateau pressure, the compliance, the resistance, all that stuff. Then we adjust individual settings to get what we want and ventilate the patient, okay? And then the ventilator delivers that ventilation to the patient. Now, when we look at your patient, your clinician, right, and assessment of physiological status, now you just adjust minute ventilation and oxygenation. So instead of setting a rate and tidal volume to obtain a specific minute ventilation, you're going to set just a minute ventilation. And the ventilator is going to assess your patient's physiological status. It's going to look at compliance, resistance, ideal body weight. And it's going to deliver the optimal respiratory rate and tidal volume in order to adapt to changing lung conditions, right? So it'll adjust those settings. It picks its own rate, picks its own tidal volume, and it'll adjust those settings based on your patient's pulmonary mechanics. And any changes to those pulmonary mechanics, it will automatically change the setting to always maintain the safest possible strategy for mechanical ventilation. AVM does the exact same thing. And this is where we get the closed loop, right? The ventilators look at your patient's compliance, resistance, ideal body weight, patient's pulmonary mechanics. It's automatically adjusting rate and tidal volume in order to maintain the safest possible strategy. So, closed loop control, right? This is complete automation of patient-derived pulmonary mechanics, right? So the ventilator is basically using machine learning, right? Because the data that's being put into it is labeled, right? Compliance, resistance, ideal body weight, tidal volume, rate. It's all labeled, right? So this is classified as machine learning because it is adapting, it is making its own decisions in what to do with your patient. Now, Hamilton's never marketed this as AI. And I didn't actually realize it was AI until I started doing research. And as I was going over machine learning, I was like, this is ASV, this machine learning, straight up ASV. And it can do full, partial, and well, passive, active, and weaning support. So basically, it can tell when your patient is spontaneously breathing, and it'll flip into a spontaneous mode and automatically wean the pressure support based on patient effort to a minimum of 5. AVM does this as well. AVM also will adjust the patient's rise time and cycle off percentage for spontaneous breaths, which ASV does not do, but Hamilton's got something for that later on. But AVM does that in addition to everything else that ASV does. All right. So goals, we want to do no harm. We promote patient comfort, and we want to get them off the ventilator as soon as possible, right? So ASV and AVM, easy to use, right? It streamlines setup, streamlines maintenance, and the weaning of the mechanical ventilator. And the best thing about it is it involves minimal interaction with the clinician and the ventilator because it's closed loop, it's adjusting its own stuff, it's weaning, it's looking at patient effort, and and this actually optimizes the workflow of the clinician. They're not have to be there changing values, switching modes, right? This frees them up to do other more important tasks, okay? And for both modes, AVM and ASV, it's all a PRVC type delivery. And spontaneous breaths are actually more of a volume cycled type of delivery. Now, how does ASV and AVM know how to do what it does? Well, it looks at Dr. Otis. So back in the 1950s, this guy, Dr. Otis, looked at all mammals, not just humans, all mammals. And he figured out that all mammals breathe in a pattern that requires the least amount of energy expenditure. Okay. Now, when you think about a patient with stiff lungs, right, what's going to take the most energy? It's for them to take a high tidal volume. So what are they going to do? They're going to take a very low tidal volume and breathe many, many breaths, right? They're going to up their respiratory rate, down their tidal volume, because that takes the least amount of energy. Now take an obstructive. What takes the most energy for that? Well, it's to breathe at a high rate, because that would mean they'd have to forcefully exhale every single breath in order to have empty lungs for the next breath. So what do? They take a huge tidal volume and they passively exhale it over a long period of time. That's because it takes less energy. Okay. And both AVM and ASV are built around this equation. And this is how it's figuring out the safest possible strategy based on your patient's particular lung mechanics. Now, last time we're going to see that guy, but I want him in your head because where is AI going? There's a possibility to go here. All right. So we have ASV, we got the Otis equation. You're inputting your percent minute volume. AVM works the same way. PEEP and oxygen. And then we have IntelliVent ASV. Now we get out of AVM. Vyaire hasn't gotten this far with their technology yet. But essentially now we're putting in what kind of O2 sats we want to maintain, what kind of end tidal we want to maintain, and what kind of, actually, that's it. So, and then IntelliVent ASV will actually set its own minute volume. And it'll adjust the minute volume based on your end tidal readings. It'll also adjust the rate and tidal volume combination based on pulmonary mechanics. And then it'll also adjust PEEP and FiO2 based on what you want your O2 sets to be at. Right? So it'll go up on the PEEP, it'll go up on the FiO2, it'll kind of stagger them, right? And this is only available in Europe. It's not available in the US. And also, you can also have it do a recruitment maneuver if it finds that it has to go up by too much oxygen, too much PEEP in X amount of time. It'll just do a recruitment maneuver and at a higher level of PEEP. So it is very, very intelligent, and it's constantly using all of this to ventilate your patient with very, very little input from the end user. All right. So as far as the ventilation controller, set by clinician, patient gender and height, patient condition, right? ARDS, brain injury, chronic hypercapnia, and tidal CO2 target, and your pressure limit for ASV or AVM. They both have a limit. And then you get end tidal, expiratory time constant, and spontaneous rate and tidal volume, right? Now, automatically adapts percent minute volume to what it needs to keep that end tidal in the range that you want it to be kept. And it achieves that by changing the respiratory rate, tidal volume, or both. For the oxygen, it's the same thing, right? You set the patient condition, SpO2 target, PEEP limit, and from the patient, you get SpO2, HLI. All right. So it automatically adapts oxygen and PEEP level to achieve what is set by our user. All right. Oh, this guy again. He's getting old, right? But he's not going away. Last thing I'm going to talk about is IntelliSync Plus. This is Hamilton Medical Technology. And basically what it does is it looks at changes in your patient's pressure and flow, little tiny changes. And this will even work non-invasively with a large leak. And what it does is it sets its own trigger. So the patient's able to trigger when they want without auto triggering. And then it sets its own expiratory cycle off. So the patient is able to cycle into exhalation when they want. And this is what helps remove phase asynchronies. Flow asynchronies, it's a matter of lack of support. So the clinician still has to adjust settings based on phase asynchronies, or sorry, flow asynchronies. For phase asynchronies, though, whether the patient is able to trigger when they want to trigger, or whether they're able to cycle into exhalation when they want to cycle into exhalation, IntelliSync can help with that. IntelliSync can do that. And what it's doing is it's taking in a myriad of waveform analysis and picking out tiny changes in flow and pressure to help determine where your patient's trying to trigger, where they're trying to cycle into exhalation. Now, Vyaire has something called AutoSync, which is what I talked about briefly before. It does not adjust the patient trigger. It just adjusts rise time and percent cycle off into exhalation, and it's included in your AVM. This is something, IntelliSync is something you can turn on or off in any mode of ventilation, including non-invasive. What it does, it looks at waveform analysis and it figures out where your patient's asynchronous, and it fixes that by either adjusting the flow trigger or the percent expiratory off, or we call it ETS, or expiratory trigger sensitivity. And this is continuously analyzing and continually adjusting these concepts. Oh, you guys thought I was gonna not do asynchronies? Well, there's a couple. So if you look here, you've got a delayed cycle at the top. And you can tell that because you have a massive pressure, you have a prolonged pressure drop before the vent actually delivers support. You should actually be getting vent support here where the green line is. And IntelliSync is taking this out and adjusting the trigger so that your patient's able to trigger when they want. For an ineffective effort, you get this little bump in flow, and the ventilator is now able to pick this out based on all the other waveforms that it's seen. And it knows it should probably adjust the trigger, right? In order for the patient to be able to trigger when they want. So this is when the patient, it takes a little bit too long for the vent to trigger the breath. This is where the ventilator doesn't even recognize the patient took a breath. But Telesync Plus can pick this out. So it does not react steady flow decrease. Okay. So if you notice here, your patient is still making effort. That's why you get this little bump and flow here. So here you would actually want a longer I time. So you would actually go down on your percent expiratory trigger sensitivity. And then you have a late cycle where the patient is trying to exhale and the vent's not letting him. You can tell by this gradual or spiky pressure waveform here. And what it'll do is it'll sense that and it'll cycle into exhalation when the patient actually wants to cycle into exhalation. So potential for good, can predict, right? Provide real-time predictions the patient needs, and you can be more proactive with AI, and you can personalize and tailor your treatment to each patient instead of kind of cookie cutter settings or cookie cutter treatments. It's tailored and personalized to the patient, which is always better. There's automated decision making. So it takes a lot of human error out of the equation. You can have improved patient outcomes. This is for both mechanical ventilation, right? And for healthcare in general. Cost savings, right? Less ventilator time, less VAEs, and less harm to the patient. Potential for evil, yeah. Pop culture, I mean, all these are evil AIs. I don't know if you've seen all these movies. We got Hal, probably the first one from 2001. We got Cortana. She was a good guy in Halo 1, 2, and 3. Halo 4, she's the bad guy. Sorry, Halo 5, she's the bad guy. Halo 1, 2, 3, and 4. Yeah. Autopilot, Wally. You got Terminator, Ultron. But you also have a lot of good AI, right? If you've seen the Avengers, you would know that Vision is a force for good. Johnny Five, who remembers that guy in the 80s? Mitchell's versus the Machines. And then you have Wally, of course. Who can't not love Wally? And then C3PO and R2D2. These are all good AIs. These are not destructive. These are not harmful. And they have a genuine interest in preserving human life. So thank you for your attention. And you guys have any questions?